Welcome to this talk. My name is Jendrik Brachter, and today I'm going to present work we've recently done on the Weisfeiler-Leman dimension of finite groups. Let me start out with some comments on motivation. So in general, there are two main purposes for me here. First of all, I want to study groups as algebraic objects and understand the key principles that determine the structure. And then there's a strong algorithmic focus. So I'm concentrating on computational aspects and algorithmic problems inside of groups, descriptive complexity, and so on. And one such aspect which is very interesting to me and which we will be concentrating on today is the isomorphism problem of, in this case, finite groups. And so given two finite groups, G and H, the task is to decide whether they are isomorphic or not algorithmically. And then, of course, we ask how hard is this problem, how does it relate to similar problems. In this context, it is always important to specify how exactly the groups are represented. So in this case, this will always be by a multiplication table. Here's an example for integer addition modulo 4, and then the multiplication relation is just spelled out explicitly. And in this form, the problem is closely related to the isomorphism problem of finite graphs, where by graph I usually mean an undirected graph without multiple edges or loops, and we will explore some of these connections in this talk. The group isomorphism problem is not known to be solvable in polynomial time, and we don't have evidence pointing in this direction really, and at the same time it reduces to graph isomorphism. So as the latter, group isomorphism is a natural candidate for an NP intermediate problem as well. Let's look at one possible reduction here actually. So we build a graph with vertex at G, and then we add in so-called multiplication gadgets for each triplet of the form G, H, and the product G times H. So they look like these, and then this encodes a multiplication relation. Here's an example. So we have all the group elements here, and then these multiplication gadgets are added on top. There's a quadratic number of them, but it's still a polynomial size reduction. And then each group element is connected to many of these gadgets. In terms of general complexity, we have this n to the power of log n bound attributed to Taiyan, which is at least from the 1970s, and this is basically due to the fact that groups have logarithmic size generating sets. And then there has been an improvement to n to the power of 1/2 log n by Rosenbaum in 2013, which uses bidirectional collision techniques. And this is, in terms of general complexity, there's really not a lot of improvement here. And this is true for almost every interesting class of groups as well, actually. So improving on this bound seems to be really hard. Comparing with graph isomorphism, in particular, the group isomorphism is still hard in practice, where for the graph isomorphism problem, we of course have nice and efficient solvers at this point. As I said, it's hard even for very limited classes of groups where much of research is being done on today. And in general, one could say that there's a lack of combinatorial or algorithmic methods which are specialized to the group isomorphism problem. So let me point out one series of arguments here which will be important for this talk, and this is dealing with substructures. So the K profile of the group G is just the collection of subgroups generated by at most K elements, or rather the multiset of their isomorphism types. And then Gowers asked how well does checking K profiles actually do in terms of the group isomorphism problem. And so this discussion started in 2011 on a blog by Lipton. Only in 2015, Glauberman and Grabowski gave the first construction of infinitely many pairs of non-isomorphic P groups, which are highly similar in terms of their subgroup profiles, that is, they have the same square root over log n size profiles. Later, Wilson gave a construction of an infinite family of groups where for each occurring order there's a magnitude of isomorphism types. And these groups have equal log n size profiles, so this is asymptotically optimal. And furthermore, these groups have a very limited structure series, so they are exponent p, that is, each element raised to the power of a fixed prime p is the identity, and this nilpotency class 2 here just means that they are structurally related to abelian or commutative groups, which have a very simple structure series themselves. And they call these groups virtually indistinguishable, because basically we have no means of telling apart groups of this family at this point. So they agree in various other isomorphism invariants as well. There's a simple specialized isomorphism test, but it doesn't tell you why these groups are actually non-isomorphic. And our contribution here is to, first of all, introduce Weisfeiler-Leman algorithms as a combinatorial and generic tool to study the group isomorphism problem, because this is very successful for graphs and very well understood. And then second, it will give us a measure of similarity of groups, which is, again, purely generic and combinatorial. And then in the second part of our paper, we have this main result that we can construct for infinitely many n pairs of groups of order n which have Weisfeiler-Leman dimension 3, so it's easy to tell them apart with our methods introduced here. But they as well have equal log n size profiles, and they also agree in some important isomorphism invariants. So these look very similar, but then using the Weisfeiler-Leman algorithm we introduce here, it's easy to tell them apart actually. Next, I will briefly go over Weisfeiler-Leman algorithms as we know them for graphs, and then define analogs for finite groups. So we are actually looking at a family of algorithms for each natural k. There's a Weisfeiler-Leman algorithm of dimension k, and the runtime is polynomial for fixed k, so the exponent depends on k here. And these form a generic way of distinguishing graphs up to isomorphism. And as such, they are used as major subroutines in practical solvers for small values of k, as well as in Babai's famous quasi-polynomial time graph isomorphism algorithm, where they appear for unbounded values of k. The idea is to color k tuples of vertices in a canonical, that is, isomorphism invariant way, and then to iteratively refine colors until this process stabilizes, and then we obtain what is called stable color classes. And then this gives rise to a non-isomorphism test just by comparing stable colors on different graphs. And with this in mind, we can make the following definitions. First of all, a graph gamma is identified by a k-dimensional Weisfeiler-Leman if it is distinguished from all other non-isomorphic graphs by this algorithm. And then a class of graphs has Weisfeiler-Leman dimension at most k if all graphs in this class can be identified for this k. So let's look at an example for k equals 2. We have the 8 cycle here, and first of all we are going to initially color pairs of vertices by the local isomorphism type. So by this I mean the isomorphism type of the induced subgraph. So in this case we have edges, non-edges, and loops. And now we are going to refine these colors in an iterative fashion by looking at how we can, so for a fixed pair we will look at color combinations obtained by each possible third vertex. So let's do this for two red edges as an example. So we have the red edge above, and for this red edge there's a blue-blue triangle through this third vertex. And if we look at the red edge down below, then there's no such triangle. So there's no third vertex connected in a blue-blue fashion to this red edge. So this information is invariant under isomorphism, and we can now distinguish these two edges actually and give them different colors. And so this is done for all the edges, and then in an iterative fashion it is repeated, and at some point we obtain the stable colors. And more formally we can put it like this. So initially we have a coloring of k tuples by local isomorphism types, again the induced subgraph now on k vertices. And then the refinement step will look at each possible k+1 vertex and refine these colors. The details are really not that important for us at this point, and anyway for logicians, which probably most people in this audience are, there's a more intuitive way of seeing these things. So let us look at standard first order logic on graphs, but equipped with counting quantifiers. And then we denote the k variable fragment of this logic by ck. And now the power of Weisfeiler-Leman refinement can be captured by this logic and also by an Ehrenfeucht-Frézé type spoiler duplicator game. So the theorem by Theorem and Immermann here is that two graphs are distinguished by KWL if and only if spoiler wins the k+1 pebble game on these two graphs, and if and only if there's a ck+1 sentence distinguishing these graphs. This generic approach is actually very powerful, so just to list some nice results in this regard. So first of all, even one-dimensional Weisfeiler-Leman refinement identifies asymptotically almost all graphs. And then there's this nice result by Martin Grohe that classes of graphs with excluded minders have bounded Weisfeiler-Leman dimension. And more precisely, for example, for planar graphs, the dimension can be bounded by 3. On the other hand, the limits of this approach have been firmly established as well. So there's this famous result by Theorem and Immermann again that there's an infinite family of non-isomorphic graphs which have linear Weisfeiler-Leman dimension. And of course, similar results for groups would be very, very interesting. But at this point, it is not even clear how to properly adjust Weisfeiler-Leman algorithms to the group situation. And that's what we will look into next. Remember that for graphs, the notion of local isomorphism was playing a central role, and this makes sense, of course, since for graphs, subsets of vertices simply induce subgraphs. But for groups, we usually have to take into account the generated subgroups, and this may make things a bit more complicated. So given two groups and k-tuples sitting inside of these groups, we could say that these k-tuples are locally isomorphic if mapping gi to hi extends to an isomorphism between the subgroups generated by these tuples. And this looks similar to the graph situation in a way, but we actually incorporate information on potentially exponentially large subsets here with respect to k. And this may be a bit implicit and hides some information maybe. So maybe there's a more explicit way of doing this, and we could call these tuples locally isomorphic simply as tuples. If basically the equality relation and the multiplication relation looks the same over these tuples. So this would be a more combinatorial maybe way of doing these things. So here we basically interpret the group as a three-edit relational structure. Now it's not completely clear what is the right notion here, and maybe there's probably a spectrum of similar notions in between actually. So what we do is we actually define several versions of Weisfeiler-Leman refinement because they all appear to be natural in their own respect. And what we do here is, of course, again, the input is a finite group, and we want to compute a canonical coloring of k-tuples of group elements. And now in the first version, we just use an initial coloring by local isomorphism types of tuples. And then in the second version, we use an initial coloring by local isomorphism types, so these two notions defined on the last slide. And the refinement step then will basically look the same as for graphs. And then we can even define a third version. Namely, we can first encode the multiplication of g in this graph gamma g. Remember the multiplication gadget, which I've shown you in the introduction. And then we also could use k-dimensional Weisfeiler-Leman refinement on this graph to obtain information about group elements. Now, it is not clear right away how these different versions interact with each other, but I want to make the point that all of them are natural in a sense again, and to strengthen this argument, we have the following result. So for each of the versions of Weisfeiler-Leman refinement for groups we defined on the last slide, we can actually capture its power again with pebble games and first-order counting logic. And these results are completely analogous to the graph situation, and so are the proofs basically. But this makes it clear for me that these things are really kind of natural on their own. And now, using these characterizations, we can compare the different versions to each other, and we obtain that we can actually fit them in a hierarchy like this. So the symbol here in the theorem should be interpreted as the algorithm on the left is at least as strong in distinguishing groups than as the algorithm on the right. And then we obtain this hierarchy of distinguishing powers. Note the drop of dimensions here for the third version. This is basically due to the layout of the multiplication gadget. So this allows for putting a pebble on a multiplication gadget, and then you can basically fix two group elements at once. But the takeaway here is that asymptotically, it doesn't really matter which version we chose. So for the dimension to be bounded or unbounded, we can use each version we like, and in the paper we will usually use version 2, so where we have the strong notion of local isomorphism as standard, but this is really not important for this talk. So for now, this is the end of our description of Weisfeiler-Leman algorithms here. And we will now look into the second part of our work, where we want to actually apply these things to obtain results on the Weisfeiler-Leman dimension of finite groups. Of course, the big question here now is, what is the maximum Weisfeiler-Leman dimension of finite groups? If it was globally bounded, let's say by some constant c, then this would mean that the group isomorphism problem is solvable in polynomial time by these methods alone, which would of course be a bit surprising maybe. But if it is unbounded, then we would get examples of groups which are really interesting and similar in a way which is now formally quantifiable, and yeah, these would make really interesting cases for the isomorphism problem. One result in this regard maybe is that if groups are not distinguished by k-dimensional Weisfeiler-Leman refinement, then at least they have the same or equal k profiles. And this is already incorporated in initial coloring basically. So in particular, abelian or commutative groups have dimension at most 2. Let me restate our main theorem at this point. So what we do here again is we construct infinitely many pairs of groups which have globally bounded Weisfeiler-Leman dimension 3 in our standard notation, but which agree in various isomorphism invariants, including logarithmically sized subgroup profiles. The idea here is to construct an embedding from graphs to groups such that combinatorial properties are in a way preserved. And more precisely, we want to encode edges as commuting or non-commuting pairs of group elements. Now, the obstacle here is that there's not really a standard way of doing this, so groups are very constrained after all. And you cannot just choose arbitrary group elements which then should commute or not commute in general. And how we chose to overcome these obstacles, and this is really a very hand-wavy high-level intuition here, is we can, in a way, force commuting relations on a small part of group elements and leave some things unspecified and basically let them generate a generic group. And so there will be these group elements corresponding to vertices where we see the edges in terms of commutation, but then there will be many other products of these vertices as well. And yeah, more formally, what we use here are finite presentations, and for some people this information may be useful, so I'm just quickly stating it here, and then I refer to the paper for the actual details. But just take away, you can see here we have generators of this group corresponding to the vertices, and then there are certain relations making this group of exponent p and nilpotency class 2 as well. And then yeah, we can give a normal form for the elements, so basically products, arbitrary products of vertices which play a role here. And then we want to apply this construction to a pair of graphs which should be hard to distinguish. So of course this means we return to this result of Theorem and Immermann again, so we use what is called pairs of CFI graphs. And let me quickly remind you of this construction. So we fix a base graph gamma, which should be 3 regular in this case, and then there are 2 steps. First of all, we will replace all vertices by the so-called CFI gadget, which looks like this. And then we will replace old edges by pairs of edges attached to these colored pairs of outer vertices here. And just to make the picture a bit clearer, I will draw this gadget in a simplified fashion like this in the following. And then we can look at a portion of our base graph here, and we will replace all vertices by the CFI gadget, and then we add parallel edges for the old edges to obtain the first graph, gamma 1, and then to obtain gamma 2, we do the same basically, but there's one position where we twist the edge. And then these graphs are non-isomorphic, but hard to distinguish, and the broad intuition here is that this twist can be moved around due to symmetries of the gadget, and it cannot be seen locally. And this similarity translates to the groups as well. So if we denote by GI, the group obtained by our construction through these CFI graphs, gamma I, then G1 and G2 have equal M profiles for M linear and the number of edges of these of the base graph basically. So they are very similar as well, and they agree in various other invariants as I've shown you in our main theorem. But yeah, we can still distinguish them using the Weisfeiler-Leman algorithm we introduced here. For the proof sketch, the idea is that, okay, we have these products in the group, we have products of vertices, and in the pebble game, putting a pebble on a product of vertices can be interpreted as putting a pebble on the set of vertices involved in this product. So we define a new game on graphs, where a spoiler is allowed to pebble unordered sets of vertices instead of single vertices only. And now the claim is that CFI graphs can be distinguished by this new game with 3 pebbles only. And I will briefly go through the intuition here as well. So first of all, here's the CFI gadget again. And actually, we use a version without colors in our construction, so this is maybe important to some. But we can still distinguish outer and inner vertices due to their combinatorial properties. And then we will look at the second such gadget, and there will be a pair of either parallel or twisted edges in between here. And let's say this is exactly the position where the twist occurs. So spoiler now will choose a set of vertices to pebble with 1 pebble. This is allowed now. And the set looks as follows. So first of all, we choose 1 inner vertex for each gadget. And then we choose every outer vertex in the same gadget attached to it, like this. And we do this for every gadget. And then we obtain a set of blue vertices. And spoiler will put a pebble on this whole set of vertices. And now duplicator basically has to answer with a set which looks structurally the same. So otherwise spoiler can find this out. Maybe duplicator can choose some other inner vertices here. Maybe we choose this inner vertex instead. But what we see here is that the number of edges covered by blue vertices does not change modulo 2, again due to the structure of this gadget. Twisting, however, will change this number by 1, so there's a structural difference in these sets no matter how duplicator chooses them, and spoiler can basically use the 2 additional pebbles to point that out. And yeah, that's kind of our main theorem split up in smaller parts. So just let me wrap things up at this point. What have we done? We defined k-dimensional Weisfeiler-Leman algorithms for groups, and we actually defined several versions of these and described the interactions between different versions. And in particular, we gave an asymptotically robust notion of Weisfeiler-Leman dimensionality. And then we apply this to groups we construct. So we construct pairs of highly similar groups with small bounded Weisfeiler-Leman dimension. And the question remains, what is the maximum Weisfeiler-Leman dimension of finite groups? So as some kind of outlook, it would certainly be interesting to establish bounds on interesting classes of groups in general. And yeah, maybe find high-dimensional examples of groups if the Weisfeiler-Leman dimension is unbounded. So overall, Weisfeiler-Leman algorithms can be applied in the situation of groups as well. And at this point, we don't fully understand its power even asymptotically, so there's certainly more interesting work to be done.